in this part, I'm happy to share with you about the fundamentals of deep recommender systems. Okay, let's go ahead. Driven by this recent advance in deep learning, and this has been increasing interest in developing the deep learning-based recommender systems. And in this tutorial, we mainly focus on the deep learning-based collaborative filtering, and where the goal is to import the neural networks to enhance the user and item representation learning. And here is the architecture of the general deep recommender systems. It mainly consists of three main components. The first component is the embedding layer, which maps the raw user item features in the high dimension space into the low dimension space. And then we have the hidden layer, which perform the nonlinear transformations to transfer the input features and learns the user item interactions. And here we can use different deep learning technique like the MLP and then all the RN, etc. And last, we have the prediction layer. And the goal is to make the predictions for specific recommendation tasks, like the weighting prediction and the learning to rank. It based on the representations from the hidden layers. Okay, hold on. And one of the most representative deep learning-based recommender systems is the neural metric factorization, which was proposed in WW 2017. Here in this paper, they explore the neural network architecture for collaborative filtering, and they devise a general framework to model the user and item interactions in different ways, like the generalized the matrix factorization, the GMF, and the MLP. And net of this proposed framework, the GMF applies a linear kernel that is the inner product and to model the latent feature interaction, while the MLP component use a nonlinear function to learn the interaction functions from the data. And note that here, the neural MF fuse these two components, the GMF and the MLP, by allowing them to learn different sets of the embedding and get a powerful, get a more powerful model. And the second paper we are going to introduce here is the wide and deep. Actually, this is very popular paper and have already applied into the industry. They jointly changed the wideness model and the deep neural network and combine the benefit of the memorization and the generalization for recommender systems. And in particular, the wide part is the linear regression for memorizing the same feature interactions, and which URIs require the careful engineering on the coarse features. And this help capture the non-linear interactions between the binary feature. And the deep part is the neural network part for generalizing to unseen the feature interactions through the no-dimensional embedding. Okay, in other case, many predicting tasks of recommender system need to model categorical variable, such as the user demographics, like the gender and the occupation. And these categorical features are usually highly sparse. So to effectively learn from this such sparse data, it's important to consider the interactions between the features. So we may all note the factorization machine, FM, as a popular solution for effectively using the second order feature interactions. And in this slide, we introduced the neural factorization machine, NeuroFM, which enhanced the FM by modeling the high order and the nonlinear feature interactions. And this work was proposed in the CIGAR 2017. And more specifically, they devised a bilinear interaction pooling to model the second order feature interactions in the node level. And then they stack the nonlinear layer about this by interaction layer to deepen the shallow linear factorization machine, and so as to model the high order and the nonlinear feature interaction and improve the FN's expressiveness. Okay, another representative deep learning-based factorization machine is the DeepFM, which was proposed in IJCAR 2017. And different from the NeuroMF, the DeepFM integrates the architecture of the FM component and the deep neural network component, so as to model the node levels and the feature interactions, like the FM, and the model the high order feature interactions, like using the deep neural networks. Okay, note that the FM component and the DeepFM component share the same feature embedding, which brings two important benefits. First, it learns both the low and the high order feature interaction from the raw features. Second, there's no need for expert feature engineering of the input, as we mentioned in the Y&D. Okay, in some scenarios, like the social network size, such as the Twitter and the Weibo, social friends of the users can provide another source to benefit users' representations. And in the social network scenarios, both direct and distant neighbors can help capture the user's preferences, especially when we consider the information diffusion process, as well as there exist users with high reputations in the social neighbors. So in this slide, we introduce typical social recommendations called DSCF, short for the Deep Social Collaborative Filtering, which was proposed in the RASIS 2019. In this model, they first generate some social sequence via the random walk techniques in the user's social network. And then they mainly employ the bidirectional long-short-term memory network, the BiLSTM, with the hierarchical attention mechanism to capture the social information from the social sequence. And such a design have two advantages. First, they can consider the information from not only the distant neighbors, but also the direct neighbors. And the BiLSTM can help capture the bidirectional influence among the distant neighbors and the direct neighbors in the social sequence. Second, the hierarchical attention here mechanisms can help differentiate the important weight of the element in a social sequence, as well as the important weight of different social sequence. Okay, on the other hand, in social recommendations, user representations in the item domain and the social domain should be heterogeneous, because users may behave and interact differently in these two domains. Then, employing the unified user representations may restrain the user representation learning in each domain. So it's desirable to learn the separated user representation in the item domain and the social domains. And to address this issue, we introduce another deep social recommendations, ratios, short for the deep adversarial social recommendation, which was proposed in the ICHICA 2019. And to achieve this goal, they use a bidirectional mapping function, which with the reconstruction between these two domains, such that they can cycle the knowledge between them to progressively enhance the user representations in both domains. However, for optimizing the ranking tasks in the recommender systems, most existing methods adopt the negative sampling techniques, which is quite ineffective. For example, in these figures, we have one male and one female. When we try to optimizing the ranking task with the negative samples, easy and unrelated negative samples are easy to be generated, like the red dress for the male and the man voice for the female. This may be helpful at the very beginning of the training process, but later, these easy and unrelated negative samples are unable to provide the useful information to further enhance the user and the item representation learning. Therefore, in this work, they propose to harness the power of the adversarial learning, the GAN, to dynamically generate informative negative sample to better guide the learning of the user and the item representations. Okay, let's take a look at this framework of the proposed methods. It consists of three main components. In this middle, this is the cyclic user modeling, and we have already mentioned. And the item adversarial learning and the social domain adversarial learning are on either side. The item adversarial learning, item domain adversarial learning on the left consists of a generator and a discriminator. Here, we mainly focused on the item domain because the social domain have similar functions. And the discriminator here in item domain is used to distinguish the real user item pair from the fake user item pair generated by the generator here. So that means the discriminator aims to distinguish whether the user item pair are related. Actually, this is a binary classification. For specific users, the generator in the item domain aims to approximate the underlying distribution of items, then generate the most relevant one. And we define the generator using the software map function over all the items according to the transfer user representations from the social domain. As the user item pair are discrete, here we mainly use the Ponzi gradient in the reinforcement learning to optimize the generator. Okay, let's go ahead. A general social recommender systems is mainly based on the user item interactions, as the deep models we introduced before. However, they mainly focus on the last click of these sections and ignore the informations of the whole sequence. That is the user's sequential behavior. So the sequential recommendation is proposed to model such the user sequential behavior, and it based on the macro trends, which utilize the sequential data by predicting the user's next actions given the last action. Recently, the existing work employs the sequential neural networks, like the recurrent neural networks, for the sequential recommendation and obtains the promising results. In particular, they propose to encode the user's historical interaction into a vector, which is the representations of the user's preferences. Using different, they can use different sequential neural network models and made the recommendations based on the hidden representations. Another represented methods in the sequential recommendations is the burst for RAG, which employs the deep bidirectional self-attentions to model the user behavior sequence. Actually, they are inspired by the success of the BERT in the MLP area, and to model the sequential information for the users. And the burst for RAG is stacked by our bidirectional transform layer. And at each layer, it intuitively reveals the representations of each positions by exchanging the information across all the positions at the previous layer in Paradise with the transform layer. Okay, although this deep learning Paradise have advanced recommender systems and have been widely deployed in industry, there still exists some drawbacks in practice. The first one is about the recommendation policies, where most existing deep recommender systems consider the recommendation procedures as the offline optimization, as well as they only focus on the short-term reward. Second, they treat each interaction as an independent instance for predictions and ignores the relationships among the instances. It may result in the suboptimal predicted performance. At last, existing deep recommender systems are based on the manually designed architecture, but it requires a lot of expert knowledge of deep learnings and the recommender systems. And it also takes a lot of time and engineering efforts. Okay, this is all for the fundamentals of the deep recommender systems. In next part, Xiangyu will present the reinforcement learning-based recommender systems.